Okay, Bismillahirrahmanirrahim, and welcome to this session. For the midterm syllabus and for the midterm guidelines, I will post one guideline video lectures probably for the midterm. So, and for the time when we could arrange the midterm exam, it can be arranged after 1 or 2 weeks. Okay, because we are lagging off a bit with the syllabus. Okay, so I have the plan to complete this basic filter design first, and then we can move for the midterm exam, since we got this advantage of online classes, because during conventional stage we have to conduct the midterm exam with the other exams because there is a exam period. However, in this case we can conduct our midterm exam individually. So I will let you know. So probably if we want to fix it at this moment, we can say, let's say we'll decide everything together. So today is 19th, so 26, then 2nd, maybe 2nd and 9th. So the week between the days between 5th to 11th. So 5th to 11th September. So you can propose the day and date for a particular day and date for the midterm exam. So altogether it might take 1 hour for the midterm, and more or less 1.5 hours for getting the question and submitting everything. So we can talk about those things later on, but the week we can conduct our midterm is the 2nd week of the September, that is from the 5th to 11th of the September. Okay. And the syllabus will be up to the basic filter design, which will also cover the all-pass filter and the filters. And we have started with the basic things of the DSP as well. Okay, let me start this with the continuation. So in the last lecture, we have talked about the general equations of an signal, arbitrary signal, and how we can start doing the filtering. Okay, so this is the same thing with a particular value, 0.1 and 0.4, and certainly of course, it should be given that which part you want to reject and which part you want to take. So since we want to reject this part, so the magnitude response should be 0 at that frequency, and the magnitude response of this frequency should be equals to 1. That is the criteria. And for this, we have taken that let the Hn, the impulse response of this system, is equals to alpha, beta, and alpha, where alpha is the 0th sample at the location. So this is at the location of n equals to 1, and this is at the n equals to 2. If that is so, then we can say that, okay, our filter looks like this, because we know that from the time domain to the frequency domain, according to the Fourier transform, the notation of the Fourier transform, x omega is equals to, we have xn and e to the power minus j omega n, and then we need to do the summation for n is equals to minus infinity to plus infinity. So we have actually done the same thing from the time domain to the frequency domain. We have write this structure, and by doing some mathematical calculations, by using the Euler's identity, we can form this equation. So this is our h omega, where we can find that this part basically represent the phase. The phase is here minus omega, and the other part gives both the magnitude and the phase as we have represented earlier. Now, for there are two conditions for 2 omega, because we want to block this omega and we want to pass omega is equals to 0.4. So based on that, we can introduce two equations for from these equations. So this is our basic fundamental equation for designing the filter. This is our filter representation. Now for this filter representation, for omega equals to 0.1, the magnitude should be 0. Putting those values of the omega, we got this equation. For 0.4, we got this equation. And for that one, definitely the magnitude is equals to 1. So this is equation number 1 and this is equation number 2. And we have two unknowns. One is alpha, one is beta. So by solving those two equations, we can find alpha is equals to this and beta is equals to this. And from there, we can write it very simply that what is our output? This is the output. Output can be written like this, because those are the coefficients, and these are the input parameters for different. So this coefficient is at the location of n is equals to 1, and this is for n is equals to 2. So from there, we can write this value of the output. The significant part is that for a particular filter, at the end, we need to find those coefficients of the filter. And we let the value of alpha, beta, and alpha, and we need to find those values. That is our fundamental ideas. Probably you could ask me that why we are taking alpha, beta, and alpha. Rather, we can also take it like alpha and beta. You should take at least 2 points for a filter. Yes, you can also take a single point alpha. That is also fine. Since we have two conditions here, two conditions are given there, we can solve two unknown parameters, alpha and beta. You can restrict up to this, and you can design your filter. No problem with that. For this example, we are just taking alpha, beta, alpha. I have followed one example, and there they are taking these 3 samples, but that is not the issue. You can even take alpha, beta, no problem with that, because the filter design is always a trial and error process. It will not give you always 100% efficiency. So all the time, what we need to do, we let something, we build our filter, and we test it with our target. If you got the response according to your target, and then you can say that, okay, my filter design is completed. So each and every time, whenever you start design your filter, a number of people can start with the same logic, but the same logic or same condition, but however, you can come up with different sort of filter design. So a number of filter design can be applicable for the same kind of applications. Okay, so in the time domain response, you can see this is your time domain response of your filter, because this is your HN. So that is the filter. What kind of filter is that? Of course, this is a high pass filter, because it blocks omega equals to 0.1 and pass omega equals to 0.4. Don't forget that what is omega. Again, omega is equals to twice pi small f. Here, this is, let's say, omega 1 and omega 2. I actually repeat these things again and again just to make you understand what we are doing here. So if this is f1, just concentrating here, what is f1? F1 is equals to f capital 1 divided by fs, where fs is common for this signal processing of your signal. So you know that what is the fs value? What is the exact fs value? If you know the fs value, if you know the value of omega 1, that is 0.1, you can find what is the exact value of f1. So that means for which f value or which analog frequency you want to block, you want to block it, or you want to reject that frequency. So with this value 0.1 represent the rational there is a I should say the frequency related to the value of fs. So that is relate to the value of fs. So you need to observe what is the actual frequency, and whenever I will ask what is the actual frequency, that actually means what is the analog frequency which represent this value 0.1. Okay, now the title is simple digital filters, and first of all we can start with the FIR filter. For the FIR filter, I always try to start with the Z-plane representation, because that ultimately help us to understand the filter design. So FIR filter, what is the criteria of the FIR filter? We already mentioned that the very fundamental criteria of this filter is number one, this is the linear phase filter, which gives us the advantage. We'll talk about this, and we only have we only needs to deal with the zero locations, not the pole locations, because the pole locations are at the center. So those are the very fundamental idea of the FIR filter. So if you want to reconstruct your original signal back after passing through your filter, then of course we need to choose the FIR filter. So for very precise signal processing after filtration, if you need to precisely develop your original signal back, FIR filter is the only option. Of course, you can use the IIR filter, and after that you can put the all-pass filter to generate a FIR filter. However, for a particular range, it might work or very close to that, but eventually it will not be comparable with the FIR filter. Okay, so we'll discuss on those issues more, because those are the fundamentals ideas of the filter design. Maybe we have learned many things, but if we do not understand the fundamental things, it's very difficult to implement in practice. Okay, let's do that. The hz is equals to 1 plus z to the power minus 1. I believe that you understand the things very clearly. 1 plus z to the power minus 1, it means that 1 plus 1 divided by z, so which means z plus 1. So always you can find that any filter representation in the z domain, it will represent the pole locations and the zero locations. So you have numerators and the denominators. So the numerators shows that z is equals to -1, and the denominator shows that z is equals to 0. What does it mean in the z plane? If we have this unit circle, okay, if we have this unit circle, then z is equals to -1 means we have the 0 at the location of z is equals to -1, and z equals to 0 means we have the pole at the location of 0. And it shows that directly by seeing this the pole and 0 location, I can say that okay, it is of course a FIR filter, because the pole location is at the center and the 0 location is otherwise. It can be in the center or any other part. Okay, it might be a complex one. We'll discuss on in other section, but conventionally it is in the real plane. We are putting it in the real plane. So by this pole 0 representation, we can find that this is a low pass filter, because we have the 0 at this location, that means it will block everything. It will block everything, and it will pass all the frequency from omega equals to 0 marching to the omega is equals to pi. So it blocks the frequency at omega equals to pi. So as long as you are far away from the omega equals to pi, it will pass everything, because you already know that how you can represent the magnitude response of a filter by seeing the pole 0 location. Okay, I do not want to repeat it again. So you can observe yourself. So if your omega is here, that means that omega equals to 0. What is the magnitude response? You can find it. What is the magnitude response at this point, at this point, this point, and this point? So all the places you can find that the distance from the pole are equal. So the distance from the pole are equal. What about the distance from the 0? You can find that we have the highest distance here, then it is reducing, reducing, and reducing, reducing. At that location, at omega equals to pi, it is equals to 0. So that means it will be definitely blocked at that point. So we have also discussed about those things. So the presentation is very simple: 1 plus z to the power minus 1. Whether it's a low pass or high pass, we'll discuss on that. Okay, why we are putting this half before that? This is just to normalize the things. So what we have, how we can got this value, we have discussed it in the other section. Okay, let me discuss it here. So from the z-plane representation, we can represent it with the Fourier transform, where z is equals to nothing but e to the power j omega. So we replace the z with e to the power j omega. And here, what we can find, if you can neglect this half, what will happen? At omega equals to 0, put omega equals to 0, we found 1 plus 1, which is equals to 2. So h omega at omega equals to 0, we found 2, which is not acceptable, because as I have already mentioned that the purpose of a filter is to pass or block, not to amplify or de-amplify the things. Okay, so de-amplification is a term, like it's a relative term, but suppression is the actual term. Yes, in the filter you can suppress the things, but h omega is equals to mention that you are amplifying the things. It is not acceptable. So then, and this is the maximum value for this filter. Okay, so what should be the maximum value of this filter? Of course, that should be 1. So then what we can do, we can multiply this h omega, where omega is equals to 0, and that should be multiplied with half to make it 1. So that's why this function should be multiplied with this half to make it maximum is equals to 1, and that is the logic. Here for omega equals to 0, we got 1, and for omega equals to pi, put the value omega there, you will find this is equals to 0. And it shows that, of course, this is the high pass filter, low pass filter. Now from this equation, if you use the Euler's formula identity, then we can write this equation as well. Okay, so you can do yourself, where we have the phase part is there. What is the phase part? This is equals to minus omega divided by 2. And where is the magnitude part? We have this one. It is exactly like the cos signal. And now we can plot the magnitude response. Here we have the omega with respect to that we are presenting, and we got the magnitude response looks like this. We need to consider that we start with the omega equals to 0 and consider it up to pi, and that is enough. So in the z-plane, what we are considering this half cycle. That is fine. Omega equals to 0 to omega equals to pi. The other half cycle will follow the same thing. Okay, so no need to run up to twice pi. As we already know that, so for the magnitude response, I again mentioned this is a magnitude it represents the cos omega divided by 2. And the phase of h omega, it comes from minus omega divided by 2. Of course, this is a linear phase. It shows that this is a linear phase. You have the phase, you have the relation between the phase to the omega in a really linear relation with the function of omega. Okay, so you can plot it. And how to find the cutoff? Definitely, whenever this magnitude of h omega is equals to 1 divided by √2, and you know that, and for that one we have the cutoff. So we have cos omega c divided by 2. So from there you can find omega c is equals to, you'll find that this is equals to pi by 2 for this example. So when this pi by 2 is half of your band, and it shows that this is a very poor quality low pass filter. However, you have built your low pass filter here. Still, what we need to find what is our Hn, because that is the fundamental output of the filter. Because whenever you need to design the filter, you need to say what is your time domain representation. That means Hn. So how many samples you need there? Okay, how many samples you need there? From h omega or from h z, we know that what should be the value of Hn. So the similar concept we'll use here. I'll talk about the phase part later on. Okay, so the same thing, you can find what is the value. Let me write hz is equals to half 1 plus z to the power minus 1. So we can write this is half, what is that, z to the power 0 plus half z to the power minus 1. So this 0 shows that at the 0th location the magnitude is half, and this minus 1, it shows that at the first location 1 we have the amplitude is equals to 1. So we have found that this is our Hn, where at n is equals to 0 this is half, for n is equals to 1 this is equals to half, and this is your low pass filter. This is the low pass filter, how it should looks like. Okay, now comes to the phase response. Okay, of course this is a linear phase, and we have found it by putting this value very easily. Okay, we have found the phase. Again, we need to extend our phase response up to pi. That is enough. So whenever we need to design our filter, what we are planning to show to the customer or the researcher, number one, the Hz, how it looks like in the pole zero locations point of view. For our case, this is a pole zero location, and also the mathematical expression, that is half, for our case 1 plus z to the power minus 1. The second thing is, what is the expression of h omega? The expression should be mentioned here. Also, we need to mention Hn, and that is the final task. Before that, we need to mention or plot the magnitude response and need to plot the phase response. I'm talking about, this is for the researcher, and for the customer, what they need the output. They need to block certain frequency and pass the certain frequency. So whenever I will tell you to design a filter, you need to show all those things: the pole zero location, the expression in the z domain, the frequency in the Fourier domain, in the time domain, the magnitude response, and the phase response. That is how you can represent your the filter design. Okay. Now, whenever we need to, as I have already mentioned, that this is a very low quality filter. We need to improve the quality of the filter. Improving of the quality filter means we want to narrow down the pass band. Where is the pass band now? This is from 0 to pi by 2. If we want to improve the quality of the filter, it might looks like this. So in that case, the pass band is reduced. If you want to increase more, it might looks like this, where the pass band is again reduced somewhere else. Okay, so how we can do that? The one process is certainly mentioned as the cascading of the low quality filters. So we have a low pass filter, and low pass filter of first order. This is first order. We have designed that and we cascaded those things, and that will improve the quality of the filter for the low pass. And if we cascade m number of filters, and if we target what is the cutoff frequency at that moment, this is the equation, because you know that this term is represent the magnitude. So for m number of blocks, that will be multiplied with m times, and that's why we have cos omega c over 2 to the power m is equals to 1 over root 2. So from there you can find that this is the general equation, and for m equals to 3, for 3 cascaded version, you can find omega c is equals to 0.2. Okay, so whenever you are increasing the order, of course it will also increase the quality of the filter. This is all about the low pass filter. What we can do, we just change the symbol. Previously it was 1 plus z to the power minus 1, and now it is replaced by the plus 1. It was replaced by the minus value. And first of all, if I ask you to draw the pole zero location, what is the starting point? The starting point of this should be like 1 minus z to the power minus 1, 1 minus 1 by z. From there we can find that z minus 1 divided by z. It is clearly stated that the zero location is now at z is equals to 1, and the pole location is again at the 0. So you can understand that at omega equals to 0, everything will be blocked, and omega is equals to pi or very close to that region that will be passed. So it works like a high pass filter. It's very, very simple. Then what is the significance of this half? It actually only works for the magnitude of the overall filter. Okay, so the maximum value you'll find 2. That's why we are putting half to neutralize that thing. I'll not cover every part of it. I believe that if you can go through this lecture, you will find it very simple. So the same things we have done here. Whenever I need something to represent, I will discuss on that particular point. Importantly, we got this equation. Okay, so that is the fundamental equation for the filter in the frequency domain. So for we also found that, okay, the omega c is equals to pi by 2 in the similar fashion. That means we have this magnitude part. Again, this magnitude sine omega c divided by 2, it should be 1 divided by root 2. From there you can find omega c is equals to pi by 2. Okay, now the thing is, where is the phase part? This will be a magnitude part. Where is the phase part? So this is your phase part. So here we have j. So the phase can be represented by this. Okay, the phase is j e to the power minus j omega divided by 2. So of course this omega divided by 2 minus omega divided by 2 represent the phase minus omega divided by 2. What about this j? This j represent pi by 2. So we have altogether the phase can be represented as pi by 2, which is common, which actually taken from this j, and then minus omega divided by 2. Okay, so this is very important. So based on that, if we consider that, what is the value at omega equals to 0, put omega equals to 0 here, then what would be the value? It is pi by 2. So at omega 0, the phase is pi by 2. You can see. And whenever you are increasing the value of omega and extended to pi, at that moment, that is pi by 2 minus pi by 2. So that gives 0. So that's why this is the final phase. And of course, this is a linear one, because this is a linear relation with omega. So that is the concept of j. J is multiplied. That means you need to add that value with that phase. Okay, so it's very simple, and that is how we can find the phase response. Similarly, if you want to improve the quality of the filter, you can improve the quality of the filter by cascading first order, high pass filter, and it will improve the quality of the filter. Okay, as we have found that this kind of phenomena will help us in future. That means if this 1 plus z to the power minus 1 gives low pass filter, this symbol change will give high pass filter, and that is true for all kind of higher order filter as well. If you have this is a single order, the first order filter. If it is an nth order filter, we can follow the same principle. We can change the location of the zero values in a vice versa, so in the opposite direction, and we can design the high pass filter to the low pass filter, or low pass filter to the high pass filter. And this is very natural because as we have found that if this is a low pass filter, and that is a high pass filter, so you can shift the zero location. Shifting the zero location 180 degree means you need to replace this symbol. Okay, so that has been shown here, that if this is a low pass filter of nth order, this is a high pass filter of nth order by changing the value. So this is plus, so we are just changing the z is equals to minus z, and you can say that whenever this is a even function that will carry the same sign. For the odd function, it will be in the opposite direction. Okay, the band pass filter, of course, you can combine the low pass filter with the high pass filter, and you can find the band pass filter. The question is, what should be the value of A? Previously, that was half. How we got that? We need to find what is the maximum value it produced. What could be the maximum value this term can produce? And then to neutralize this, we can do the inverse of that, and that is the value of A, and that will be shown in a minute. So from this equation, you can write this equation as well. So this is in the z domain, and this is in the Fourier domain. So after writing this, what we can find, we need to find out where is the maximum. So we need to find the maxima of this, the maximum of this function without putting the value of A, and we have found that the value is 2. The maximum value is 2. You can find the maximum value. Since this is a sine function, it is very easy to find where is the maxima, and from there you can find, okay, 2 is the, so because here the sine omega, what is the maxima of that? the maximum is 1. So 1 into 2, that gives the maximum is 2. So what should be the value of A? So A must be is equals to half. So we can replace the value A with the value of half. Okay. So this is the fundamental equation to draw the magnitude response. However, by the pole and zero location, you can draw both the magnitude and the phase. But conventionally, we write this equation to draw the magnitude and the phase response. If you can consider that the A is equals to half, so this will cancel each other. So what is the magnitude part? The magnitude part is this. So H omega magnitude, it represents sine omega, and the phase of this, what is the value? That is J. J means pi divided by 2 and minus omega. That is the phase. Okay. So we have wrote this magnitude response. You will find the magnitude response looks like this, and from the z-plane representation, we found that the zeros are there. And what about the poles? These are the poles, and we have 2 poles. So whenever you have multiple poles in a single place, you can represent it like this. So you have the single symbol and write the number, how many poles are there. Okay. Whenever you have the single pole, no need to put 1 over there. Okay. They are the single zeros, so no need to mention how many zeros are there. Okay. And okay, here I have one mistake. As I have already mentioned, that what is the phase? The phase is J first. J means pi by 2 and then minus omega. That is the phase response according to the equation. So now at omega equals to 0, what should be the value? The value is pi by 2 minus 0, so that is pi by 2. So this phase response is not correct. So the phase response, if we can draw here the phi at omega equals to 0, this is omega, what should be the value? Pi by 2. So it will start at pi by 2 positive. And now at omega equals to pi, that is our final destination. This is a pi by 2 minus pi. This is of course minus pi by 2. So it will say this is our pi point, and this is minus, let me choose another color. So this is, let's say, minus pi by 2 point. So this is the point. At omega equals to pi, the phase value is minus pi by 2 according to the equation. So the phase response should be looks like this. Of course, at the location of omega is equals to pi by 2, that is equals to 0. Okay. So just follow this, this one. Okay. So we have mistake here. So we start at 0. So you can change it that. Okay. So we can correct it very quickly by this. This is pi by 2 plus, and this is minus pi by 2. Then it is okay. Then it is okay. And this is 0, 0 at the location of pi by 2 of omega. Okay. I believe you understand the process. So whenever you understood the process, it's very simple task to do. Okay. Band stop filter. Okay, so the thing is very simple. Previously that was 1 minus z to the power minus 2. Now it will be that will be plus 2. And band stop filter, where is the in the band pass filter, we have this. In case of band stop filter, we have the things like this. Okay, So the zero locations are now complex, because at that moment, at omega is equals to pi by 2, everything will be blocked. The zero shows that where you are blocking the things. Okay, so this is at the location of pi by 2. Okay, so similarly, you can write this equation, and from there you can draw the magnitude response. Okay, one thing need to be very clear. This is the first time we have found that, okay, whenever this magnitude try to pass, so for all other cases we have discussed earlier, for the low pass filter, for the high pass filter, and also for the band pass filter, everything is like this. There is no crossing. Okay, from 0 to pi, there is no crossing. Now we have the magnitude is crossing the 0. So naturally it should be like this. As we have mentioned that there is no negative magnitude in case of filter. That's why we need to convert it in the positive direction. So that is the magnitude response. What about the phase response is very important. What is the phase response from this equation? That is minus omega. The phase response of h omega is equals to minus omega. Of course, that is a linear phase. And so it will start with the 0, going like this. Whenever we have this crossing, it should add 180 degree or pi, you can say pi, and it will be there, and then again it will be reduced like this. So this is the folded version. I also mentioned that you can go for unfolded version as well, no problem with that. However, conventionally we always represent it with the folded version. The unfolded version, no problem with that. Okay, you can do that. Sometimes the unfolded version gives you better understanding, but for the representation we always use the folded version. Okay. Okay. Now moving to the IIR filter type. Why we should move to IIR filter type rather using the FIR filter type. So the notion to use the IIR filter is that the controlling of the filter from the point of view to improve the quality of the filter is much higher. The quality means the quality of the quality to reject the signal and to block the accept the signal. That is the quality. There are different sort of quality of the filter. If you think that from the stability point of view, that is one quality. From accepting some signal and blocking some signal, that is a quality. The order of the filter, that is one quality. The signal to noise ratio at the output, that is one quality. And the linear phase response is another quality. So that's why there are different sort of quality. So we are talking about the quality where by using same number of poles and the zeros, we can improve the higher quality. For example, in case of FIR type filter, if you want to improve the quality of the filter, certainly what you need to do, you need to cascade the things, okay, from single order to first order to second order, third order, and so on and so forth. However, in case of FIR filter, just changing the pole location or the zero location, the pole location or the zero location, you can change the quality of the filter. We'll see that. Okay, so we start with previously, if you can concentrate, we only deal with this part, the numerator part. Now we are representing one pole which is not in the center. Okay, so the HZ plane representation made it very clear. So previously we had the pole 0 here, and the pole at the center, which represent what? The FIR type filter. Now this pole is now shifted to there, and that actually may converted our FIR filter to IIR type filter, which also mentioned that in FIR type filter there is no feedback, but in case of IIR type filter we have the filter. Whenever we have the filter, we have something in the denominators. How many feedbacks you have here? We have single feedback. That's why this is a first order FIR type filter. If you have two feedback, let's say we have 1 minus beta into z to the power minus 1, that means we have two feedback, and we may have another pole. Maybe we have another poles there, so beta, and whenever we are introducing another pole there, maybe we also have another 0. Where at the 0? Maybe at the center, whatever the case, but we need to introduce the 0. Make it very simple. We are just introducing the pole not at the center, rather than center. That is the IIR filter, the very simple first order filter. If I ask you what kind of filter is that, low pass or high pass filter? This one is low pass or high pass filter?
Low pass filter.
Yes, thank you. This is of course low pass filter. By seeing the location of the 0, because 0 is at the location of omega is equals to pi, that is at the higher frequency, high frequency. So high frequency must be blocked, and omega equals to 0 should be passed. So the passing and the blocking basically depends on the location of the 0. If I put another 0 there for the same filter, if I put another 0 over there, of course you can say that, okay, this is now converted to a band pass filter. Okay, so restrict to this low pass filter. Again, this is the pole for the pole 0 location. Now this is the z plane z transfer function with the z value. We are putting this in front of that. So how we can choose this value? As we have know that we have it is known to us that where we will get the maximum magnitude by this z-plane representation, where at which location we should get the maximum magnitude. Of course, at omega equals to 0, no question about this, because that is the maximum distance from the 0 location. That's why at omega equals to 0, considering this equation part, we have found that the value is 2 divided by 1 minus alpha. So that is the maximum value. So what should be the counterpart? The counterpart should be 1 minus alpha over 2. So this equation, sorry. Just a moment. So this equation should be multiplied with 1 minus alpha divided by 2 to make it normalized. Okay. Otherwise, the maximum value shows as 2 divided by 1 minus alpha. Okay. So that is how you can find this value. So this is a normalizing function or constant. Afterwards, we actually follow the same things what we have done earlier. So for the magnitude response, we just square it of the modulus value of the filter function. So whenever we have done it, we have found this equation at the output. If you want to plot it here, the magnitude response, what we have found, whenever we are this equation, and based on this equation, so whole equation, so if we change the value of alpha, what is the value of alpha? The value of alpha is the location of your pole. So this is the value of alpha. If you change the value of alpha, increasing the value of alpha, that means you are shifting this alpha towards the unit circle, then the quality of the filter will improve. For alpha is equals to 1, you have poor quality filter. Alpha equals to 2, that means, let's say I'm putting 3 poles. So this is for alpha 1, this is for alpha 2, and this is for alpha 3. You can observe that, and the quality of the filter will improve by changing the pole location. And as we have found that there are some online tools by which you can also observe this kind of situation. And this is okay. Let me show this. So the link, I will give the link in the in your whenever I will upload the video lecture, you can find this one. Fundamentally, it looks like this. Maybe I can reload the things how it looks like. Maybe it takes a bit time. Okay, so at the beginning you'll get this kind of essence. This is micromodeler.com. So I will give you the link, and you will find some other sort of so this is the link, and you'll find everything. Let me show. So maybe I have covered almost the full window. So what we need here, we need the z-plane representation, the transfer function, so how the transfer function looks like, and this is the graph and the plot, and also there is 2 graph and plot, so the time domain representation. So here we have different sort of parameters are there. You can play with this. So at this moment, what I want to show you is only the things we have already covered. Maybe. Okay. So these 2 things are very important. Also these 4 windows maybe good to see. Okay. Yeah. So first of all, take the blank filter. Okay. And we can also talk about the Butterworth, Chebyshev, inverse Chebyshev, Bessel filter, and epileptic filter. Maybe in the after the meet we'll talk about those filters and design of that. Okay. By clicking on this, you can shift the axis as well. Okay. So we need the axis from 0 to 0.5. They are representing 0 to 0.5 is 0.5 represent the pi value. So first of all, if we want to represent the okay, real 0, you can put the real 0. Let me put it here, and the real pole at the center. So what kind of filter is that? Of course, this is a low pass filter, and whether this is FIR or IIR type filter, let me show that. If we target what is the magnitude, only the magnitude response, this is the magnitude you can find. Okay, you'll see that magnitude of the filter. If you change the 0 location, try to see that, you'll see this is of course a high pass filter, and you have changed the magnitude response. Similarly, you can look at the time domain representation as well. This is very interesting. This is for the high pass filter. You have half and half, okay, in the time domain. And for the low pass filter, very basic low pass filter, you have half, positive half, and positive half. So we have shown it in the earlier discussion. Okay. What about the phase response in case of a low pass filter? This is for a low pass filter. This is a phase response represent. So you click on that. So that shows us the phase value. Probably I haven't put this the center. Maybe I need to, yeah, now it is at the center. If I want to see this phase, you can see that the phase is a linear. Of course, that is a linear. And if I change it to the high pass filter, the low pass filter, sorry, yeah, high pass filter, still you can find that, yeah, I'm talking about the only the phase. So you can find that the phase is also linear. Now about the magnitude response and the quality, what is our main concern at this moment? If we go for the magnitude, try to see that this is a conventional, very poor quality low pass filter. Now, if we change the location of the pole, you can see that, yes, the quality of the filter is now increasing. The quality of the filter is increasing. So how you can increase the quality? Whenever it is actually, you are increasing the value of alpha, you can increase the quality of the filter. Of course, you can follow the time domain response as well at the same time. Okay, so just changing the time domain responses, you can practically implement that. However, if I now introduce the phase, just look at this. Previously that was linear. Now whenever you are increasing the quality of the filter, unfortunately the phase is now became non-linear. You can't go beyond this. Okay, so can you see that whenever it is very close to unit circle, the quality of the filter is at its best. However, if I move after 0, what you can see that, okay, from the magnitude response, okay, still this is fine. But what about the time domain representation? You can see that this actually gives an unstable situation. Of course, this is unstable situation for the causal system. So look at this time domain representation. Keep tracking the time domain representation. Still, this is unstable, and whenever that is inside the unit circle, that makes the system stable. So we need to trade off between the quality and the stability of the filter. Okay, one more thing is here. In this section, we have the structure of the filter. What does it mean? If I can show you here, this is the structure of the filter, as well as you have Z domain representation, pole zero representations are given here. Okay, the equation is also made, and also you can put to the code, and you got the code here. This is in the C platform. So whenever you got this code, you can convert it to the machine language, any language as well. They are the converter of that one, and you can burn it in the microcontroller or the microprocessor, and you can design. You have implant your own filter for a particular purpose, for the image processing, for the robots, and whatever you need. Okay, so from the sensor, you are collecting the signals, and from there you want to process something practically. So what you need to design your microprocessor with this kind of filter. So in practice, what you need to do, you need to actually implement the I should say the logic which actually build the transfer function in the time domain. So at the end, as an engineer, you need to know this one, only this one, this time domain representation. What are the values are there? Okay, so you need to build your transfer function like this. Then whatever the inputs are there, it will do the convolution with this. The convolutions will be done, and after that you will got your the expected result. Okay, so this is very simple, but very important for understanding the filter and the filter design. Okay, hopefully that will help you to understand, mostly understanding the filters. Okay. Let me go back to our original lecture slide. Okay, rearrange the thing. Okay. Okay, probably you have got the idea how the quality of the filters can be improved in case of IIR filter. You do not need to cascade the things, and even by cascading the things, you have a very little control over the quality of the filter. But in case of IIR type filter, you have full control of the filter from the quality. We are precisely mentioning that which frequency you want to accept and which frequency you want to block. That's why this IIR filter is so popular. Okay. To find the cutoff frequency, of course, this part shows the magnitude. Then this magnitude, this is a square of h omega, the magnitude square of that. So what should be the magnitude? Magnitude 1 divided by √2 whole square. It's very simple. You can find what is the value of omega c. Okay. For a given value of omega c, so whenever the customer give you some assignment, or your boss give you the assignment, so they will mention the value of omega c. We can find that what is the relation between alpha and omega c from this equation. This is a fundamental equation. What is alpha? Alpha is equal to, so since this is a second order equation, we got the two values. Okay, of course the alpha, as I already mentioned, that for the stability the alpha should be less than 1. So if that is so, of course, what is the maximum value? We already know that the maximum value of sine omega c could be 1. So 1 plus 1, it will be more than 1. So that's why 1 minus sine omega c over cos omega c is acceptable. So plus 1 plus sine omega c is not acceptable for a particular value of omega c. Okay, so for omega c is equals to pi by 2, alpha is equals to 0. What does it mean? Omega c is equals to pi by 2 means that is a very low quality filter, what we have seen earlier. So this is the result. This is pi by 2, this is pi, and this is 0. This is 1 divided by √2. In this case, the alpha is equals to 0 means that is at the center. We have already proven that. Okay. Now, if we change the value of alpha, the location, it will improve the quality of that. Okay, for the high pass filter, the things is very simple. What we need to do, we need to change the shift the things. Here, previously it was positive, now it is negative. Previously it was negative, now it is positive. Okay, that is the task we need to do here. Okay, so just follow the process. I believe that is a very simple task. So everything is like the previous one, and you will get the same thing here. So again, from the pole zero perspective, we have the 0 there. Whenever we are shifting the poles close to the unit circle, it will improve the quality of the filter. The similar patterns we have found here. Okay. Now this is the bandpass filter. Maybe we can start the bandpass filter in the next day. Okay, so that will be a good starting point for the next class, inshallah. So okay, we'll start it from the next class, the bandpass filter, and try to cover up to, so try to finish up this basic filter in the next class, inshallah, if possible. And then 1 week we can elapse for the reviewing the things, or we can give you some tasks from the book. There are some the Procteus book, there are some exercise problem. So I will mark some exercise problem so that you can go through those, particularly in the chapter number 1, 2, and 3. So I'll give you some problem, maybe by next week, so that you can go through those problems for the midterm. Yeah, you also you will also find the solution in the websites in different sources. If you search it in the internet, so you can go through the solution. First of all, try to solve yourself. If that is problematic, you can go through that solution note as well. Okay. One of our friend or classmate here, Aldi, he is suffering for COVID, so we can keep him in our prayers so that he can recover early and completely soon, and he can join with us again. Okay, so do you have any question or comments on today's lecture? Okay, it seems everything fine. Okay, thank you for your presence.